Okay, welcome back, everybody. We are now in week 15 of BACS. Wow, it's been a super long semester, right? And I know the disruption of having to stay at home is making it even harder. So, the good news is we only have two more lectures left. And today is our 15th lecture, so we will have week 16 a lecture and a homework also next week. And then week 17 will be a free lecture. It's a free lunch. You can come, you can listen. We'll just talk about some miscellaneous topics in computation and coding, but it will not be associated with any homework. Okay, so week 17 is completely optional and it's just for those of you who kind of want to carry forward a little bit what you're learning, learn about some new tools and things like that. So that'll be week 17, and there will be no exam on week 18. So I hope you're happy about that. At least I hope you're not sad about that. Okay, um, so let's slowly get started here. Okay, all right. I'll ask once again that those of you who can, please turn your webcams on so that I can see you and feel like I'm talking to real people. It really helps me and it lowers my fatigue as well. Okay. Once again, if you have questions, please do raise your hand and uh, or you can type into the chat window. But if you raise your hand, then I can also see, I get a little notification that someone has raised their hand, so it helps me. All right, great. Thank you so much. Great. So week 15, let's get going. Thank you for getting the homework done. And there was three questions on the homework this time. It looks quite long, but I hope you found that the three questions were all rather short, just several things to cover. Okay, so I'll try to kind of review what we did on the homework while I also introduce some new topics. So let me get started. So let's start with this mediation example that we saw last week. In this example, we had several variables that we were using trying to explain miles per gallon in our cars data set. By the way, for those of you who are going to perhaps move on to data science careers or analytics careers, the CARS dataset, or the MT CARS dataset as it's sometimes called, is a very well-known dataset, and it's one that you can always talk about with your colleagues and say, yeah, remember in college when we played with the CARS dataset? It's going to be a common point of discussion for many of you, and you'll feel like, yes, we went through the same thing together wherever in the world you were learning these topics, okay? Though I don't know that every school teaches it the same way that I'm using to teach it. They may be using it for different purposes as well. All right. So, okay. So we were looking at the cars data sets still, and perhaps for the last week. And we were trying to regress miles per gallon over several variables: weight, acceleration, model year, origin, and cylinders. And what you and if you run this, let's take a look at where we are. Oh, well, hold on. We have to do mediation. Okay. All right, let's do this one. Okay. So let's load the cars data set. Okay. And if we run a model where we regress miles per gallon over one, two, three, four, five separate variables, what do we get? Um, let's see the summary of this. And these are our results, okay? And I should have them on screen here. You might notice some unusual things though, if you look at this carefully, particularly if you compare it with the correlation table of all these variables, miles per gallon, and the five variables we were using to explain miles per gallon. What you'll notice is that some of these variables, like log cylinder, for example, well, that's the one we're really interested in, it has a negative regression coefficient against miles per gallon, but if you and it's about minus 0.05. If you look at the correlation table, however, you'll see that cylinders, its correlation with miles per gallon, it's very large. It's like minus 0.82. It's almost as large as weight, which we know is one of the most important things in this regression example. So how did it suddenly go from having such a large correlation to such a small regression coefficient? This is potentially, again, a sign of multicollinearity, that cylinders must be correlated with something else that is explaining miles per gallon well. And so as a result, regression can't give both of them equal credit, so it's giving it all to the bigger one. So it's giving it all to weight, and cylinders is getting next to nothing. And this is okay for some purposes. If we were only going to use regression, for example, for prediction, to predict miles per gallon, it might actually be okay. In prediction, multicollinearity like this is not a big deal oftentimes, as long as someone gets credit for the variance explained. However, if we're trying to explain how cylinders affects miles per gallon, this regression is unsatisfying. We cannot go and tell people in good faith that cylinders has a very small negative effect on miles per gallon when we know it has a very high correlation. Okay, and we can get another glimpse of this multicollinearity if we run a VIF analysis on it. And we see VIF values that are kind of large for weight and cylinders once again. Like, as we mentioned last week, I consider between 4 to 5 to be kind of large. Okay, so we do have multiple indications that we have a multicollinearity problem here. And how do we resolve it? In previous weeks, we resolved it in this kind of an example by simply dropping explanatory variables, by saying, well, let's just drop cylinders, or let's just drop weight, let's just drop a few things. And one thing I said last week is, well, there's something else we can do other than drop things. And one of the things that we can do is that we could, if we have some theoretical reason to believe that cylinders affects miles per gallon, not directly, but rather indirectly through some other variable, we can model this as a mediation. So let's take a look at that. So in the mediation example, cylinders affects weight, and because it affects weight, it affects miles per gallon indirectly through weight. So here I'm presuming some kind of domain expertise. Maybe I've talked to some car experts or something. I didn't, it's just an example. But maybe I did, and I have some solid feedback telling me that really cylinders affects weight, and the weight affects miles per gallon. So that's maybe the way I should be modeling it as a causal explanation. Okay. So then what we can do is we can remove cylinders from the regression and simply model miles per gallon over weight, not cylinders, and everything else that we were interested in. Okay. So we do that, and we can get a summary of that. And okay, everything looks good. Weight still has a strong negative, about 0.87 or 0.88 coefficient, and acceleration modelier and other things all have certain effects. Okay. Um, what we can do next is, now that we've removed cylinders from this causal model, we can create a different model where we model what we know that cylinders does, which is that it influences the weight of the car. And to do that, we simply regress we regress weight over cylinders. All right. So we regress that. And here we notice that, yes, cylinders has a very strong correlation with weight. So it's going to have a strong regression coefficient in the simple regression as well. All right. So we can do this. And then the last step of this little magic trick is to understand how cylinders affects miles per gallon through weight. We can simply multiply these correlations. So we can start on the left. The correlation to weight is about 0.82. The correlation from weight to miles per gallon is minus 0.88. We can just multiply these two together, and we can see that the indirect effect of cylinders on miles per gallon is minus 0.72. Right? So that gives us some indication of how cylinders affects miles per gallon, and we can report this much better than reporting minus 0.05. That's unbelievable, right? So now we have some kind of an explanation, and we have coefficients for um, all the variables of interest, and we even have a coefficient that we can report for the indirect effective cylinders as well. So from an explanatory point of view, this works so much better than having multicollinearity and just dropping variables. All right. There's one more thing to this story, which is, unfortunately, when we multiply like this coefficient times this coefficient to get the indirect effect, the confidence interval of this indirect effect is not always clearly understood. It can be a little bit complex depending on certain situations. And we can fall back on our old friend bootstrapping to save us here. So what we can do is we can simply create a bootstrap function, which I asked you to do for this homework assignment. And what we will do is we will just rerun the two regressions, the direct effects regression from weight, acceleration, model year, and origin to miles per gallon, and the indirect effect from and the direct antecedent effect from cylinders to weight. We can run these two regressions again over bootstrap samples, and we can keep computing this product, this indirect effect. We can keep computing it over every single bootstrap. All right. So we've got this, and let's run this bootstrap. It's going to take a little while to do because it's got two regressions to run 5,000 times. But once it's done that, we can then examine where do, say, 95% of the indirect effects lie, and we can visualize it. All right. So this should run for just a few more seconds here. And now we can ask directly these indirect effects that we got. So if we take a look at these indirect effects, there's going to be a whole bunch of indirect effects, about 5,000 indirect effects here, all about minus 0.6, minus 0.7, something like this, it looks like. But let's take a look at the middle 95%, and we're told that the middle 95% is somewhere between minus 0.78 and minus 0.65. So that gives us, if we wanted it, the 95% confidence interval of this indirect effect, okay? And we can plot the density curve of the density plot of this indirect effect, these bootstrap indirect effects, and we can actually visualize the 95%. So 0 would be considerably far away to the right, where we actually have a fairly small confidence, a tight confidence interval here. So we can say with pretty good, we can say with fairly good confidence, if you will, that the effect should not be 0. All right, great. So this was our conclusion about mediating effects, right? And one more look at our good friend, the bootstrap. And this helps us resolve a particular type of multicollinearity issue that we would have if we didn't model it this way. All right, great. Any questions? I'll take a little drink break here. All right, so let's move on then. That was mediation, and I might come back and touch upon it again next week. Maybe, maybe not. We'll see. But for now, I want to go back to the big topic of last week, which was PCA. Okay. Now, over the weekend, I created a little tool that I wish I had made last week because it's a little bit of fun to play with. All right. So let me go try to find it now. It's going to be, where is it? Somewhere here. All right. And I made this little tool called Interactive PCA. If you remember our interactive regression examples, this is the PCA version of that I've made, okay? So what it allows me to do is help you visualize in a little bit more of an interactive way this time what PCA is doing, because that was one of the big topics of last week. So let's try to take a look. So if we have a data cloud, and let me start drawing a data cloud out for you, okay? So I'm going to start drawing a data cloud. And what you can see that PCA is trying to do is it's trying to find out the dimensions, the important directions in which there is variance in this cloud of data, all right? And the the longer vector here is showing you the first principal component. Actually, the first principal component and the second should start from the origin. I've just shown you the negative side of them as well. But the origin in this case would be the mean of our data set. So from the mean of our data set, because we scale our data, we can see the direction of major variance as the first principal component, which I've shown as a solid line here, all right? Apart from that, what is the other important dimensions in this data set? Well, first of all, this is a two-dimensional example. There's only X and Y. So there's only going to be one other direction in which it could stretch, which is orthogonal or 90 degrees to the original direction. So the other dimension, which is important and unrelated to the first principal component, is the second principal component. And it's got a vector. It's shown by this vector that starts from here and it kind of stretches out this way. All right. Last week we talked about eigenvectors and eigenvalues. These arrows I'm showing you are not really eigenvectors because eigenvectors would have length 1. What I've done instead is I've scaled the eigenvectors so that they're scaled by the standard deviation or variance of the direction that they're pointing in, basically by the eigenvalue. All right. So I've kind of shown you a larger vectors, which are scaled eigenvectors. I've just scaled them up so you can see them clearly. And they're basically pointing in the directions of major variance, okay? So if I draw this little egg shape here, then you can see that PCA is able to tell me quite nicely what are the major axes of these egg, all right? The bulk of our data should probably be in the middle normally, all right? Okay. Now, I had this question last week, which is, well, what would happen? I think it was Yenu, was it you? About what would happen um, if the second principal component was bigger than the first principal component. Well, and I mentioned it can't be because by definition, the first principal component points in the direction of major variance. But let's play along. Let's stretch this the other way by accident. Let's make this egg actually stretch it out in this direction. Do you see what's happening now? The first principal component is now is slowly turning and pointing in the direction of major variance. So if I stretch it in a different way, then my principal components just spin around and point so that the first principal component is pointing in the major direction of variance, all right? And this is essentially what PCA is doing for you. All right, excellent. So that's a visual demonstration of what PCA does, okay? Now, it looks really pleasing when I draw data clouds that look like eggs because everyone, including you or I and the computer, can all look at it and agree which is the major axis. I should warn you that the directions in which the principal components are facing in some rare circumstances may not actually be very intuitive for a human being, but it's very intuitive for a computer. And an example of that I've drawn is right here. All right. In this case, I did this again last night. I just tried to play with it to try to fool PCA, but I'm actually fooling myself, where I tried to draw this shape where to a person like me, a simple human being like me, it looks like at the two axes, one should be going top to bottom, the other should be going left to right. However, PCA is looking at it in a completely different way, and it's twisted itself and pointing in directions that are not intuitive to me. All right. So don't assume that PCA always has to point in directions that human beings recognize or think is intuitive to us. We have a sense of up and down, left and right that may or may not match what variance tells in this case. All right. Now, I do have to tell you that I had to engineer it quite a bit to make PCA face in a strange way like this. If I try to do that by hand again, I'll show you it's actually quite difficult to get myself into that kind of a position. So here's my PCA example where drawing something like a upside down T. And you'll see for the most parts, oh yeah, as you can see here, well, here PCA is actually doing a pretty good job of corresponding to the two um, lines that I'm kind of plotting out. I have to get a little bit sneaky to figure out exactly how to get this to twist around. There we go, finally. Got it. I fooled it. But like I said, I'm actually fooling myself because to me as a human being, it looks like an upside down T, which is just a couple of points out of place. But to PCA, it's saying no. If it looks at it from a variance point of view, then the um, principal components are actually almost 45 degrees to the two lines I'm kind of plotting out. Okay, so but as you can see, it's not easy to get myself into this situation. But hopefully the point of this exercise is to let you know that PCA can, or these eigenvectors and eigenvalues can be kind of intuitive, but there are times where it may not be. All right, and this is just a visual example of that. All right, cool. If you want to play with this, I made a little R package that you can install. It's not available on CRAN, so you would actually have to install this special package first called DevTools. DevTools is a package that allows you to do a whole bunch of things with packages that is um, outside of CRAN potentially. And in this case, you can use the DevTools package to install my package from GitHub. So I've posted the code on GitHub. You can install my package from there. You have to load this library then called comstatslib, and then you can run this function. All right. So I should have put it up online already if anybody would like to play with it, or I'll try to get it up at least after this lecture if it's not already available. Okay. So I hope that was an enjoyable demonstration of what PCA is essentially doing. All right, so it's trying to point at the directions of major variance. Any questions on this so far? All right. I'm not really going into in this class into how this PCA technique finds these eigenvectors and eigenvalues. There's a couple of different major techniques, but potentially more, of how it kind of discovers these vectors and how it kind of does the algorithm and the math to find it. All right, but I'm not really going to go into them because I want to spend more of our time in this class exploring how to use it rather than exactly how it works. I will mention that there is a couple of really major ways in algorithms that it uses. One is called EVD, or eigenvalue decomposition, which is a technique to find the eigenvalues and eigenvectors directly from the covariance or from the covariance matrix of the data that you have. There is another popular technique called singular value decomposition, or SVD, which also actually ends up finding just about exactly the same thing as eigenvalue decomposition. Okay, and they'll give you very similar results with one potentially big difference, which maybe I'll mention later. All right. Okay, so how how do we use this technique? And it's kind of nice. It's for some of you it might be your first, or not first, maybe after regression, glimpse at how a computer can find relationships in data. We saw that ANOVA or regression can do that as well, but PCA is another way in which we can computationally find relationships in data. Okay, and it's unlike regression and regression lines, it doesn't favor one direction over the others, or it shouldn't. In regression, we were trying to explain a y variable, so we were always trying to minimize our errors in the y direction. Whereas here, we're trying to minimize errors in every direction, and we're not favoring any direction over the other. All right. So this is PCA. And how do we use it? Well, last week we saw a couple of examples of how to use it, and I want to kind of show you one example here. Okay. And you did this for your homework, so this should look familiar to you, where we used it as a dimension reduction tool. When we have multiple directions and multiple dimensions in our data, and we just really want to collapse it down into fewer dimensions for various reasons, of which we saw in the homework, and we'll talk about more right now. We can use PCA, okay? Now, before I get into that, I want to give you a little demo of something that is a little bit of a segue, a little bit orthogonal to our topic of PCA, but it's something that I think some of you might enjoy, all right? I'm going to start this demo, so let me close this up. I don't need this window anymore. And let me go to my dimension reduction problem, and let me wipe out the plots and clean up my working space a little bit so that I can see what I'm doing. Okay. So let me read this cars data set in for the 100th time. I don't know how many times I've loaded this into my computer. And what we said on the homework we want to do is we have these 4 dimensions which are highly collinear: cylinders, displacement, horsepower, and weight. They're all kind of sort of explaining the same thing, and we can't put them into the same regression model because of multicollinearity problems. And so earlier on, we just dropped all of them except for weight, and we just used weight, and we said, we lose some stuff, but what can we do? I think that week, one of you, I think it was Guild, asked me, but isn't there a way we could put them together in some way and like use them all together? And the answer is yes, there's multiple ways we can put them together. And you saw one of them on the homework assignments, okay? So let's take a look at that. Here are the variables. And what we're interested in particular are these correlates, all right? These correlates, these 4 variables correlate with each other, okay? And let's take a look at them, correlates. And here comes the little segue, the little diversion I wanted to talk about really quickly. So here are the correlates. You notice it's showing it to me in 7 decimal places, a little bit more than I wanted. So then I could just round it to 2 decimal places, okay? Now, forgive me as I go on a little bit of a tangent here, all right? As you can see, oftentimes in R, we have to like write code that it becomes a little hard to read and understand the intention of what we're trying to do. In this line of code here, if we read it from left to right, it reads a little weird. It's saying, please round the correlation of my correlates to 2 decimal places. Well, actually, that doesn't sound too weird, but if you try to understand what does this line of code do, it can look a little bit unclear because it starts with rounding. But really, rounding is the last thing I want to do. What I really want to express is that I want to take the correlation of these correlates, and then I want to round them to 2 decimal places. So sometimes, because R is written as functions within functions within functions, it doesn't read very well because you end up reading the last thing you're doing first. And the first thing you're doing is like somewhere deep in the middle of your line. So unfortunately, sometimes R can make things a little hard to read, okay? And for that reason, when you are doing your peer reviews, you'll notice that some of your classmates are using a special package called Margritter, excuse me, I always say it wrong, and which gives you a nice little pipe function, all right, which allows you to kind of rewrite lines like this from left to right. Well, a couple of weeks ago, the R programming language added a simpler form of piping directly into the language. So it's now a native part of the language as of a couple of weeks ago. So if you install the new and latest R, I think it's version 4.1 or something like this, it has a native pipe function. Let me show you what that looks like. It looks something like this. So this same line of code I wrote a moment ago, right? Round correlates, comma 2, I can write it like this, right? So here, what you're seeing is I'm taking my variables called correlates, and then I'm piping. This is called a pipe, all right? And piping means we're kind of sending them through the tube to the next thing. And we're sending that to the correlation function, right? Notice I don't have to put correlates within the core function because the pipe, what it does is it takes what's on the left-hand side and it puts it as the first parameter of the function on the right-hand side. So it kind of puts it into this correlation function for you, okay? And so that this part produces the correlations. So if I just do that, I get my correlations. And then I can do one more step. I can say, well, now pipe this to the round function, and I can tell it to 2 decimal places. And what it does is it takes the result of the correlation of the correlates, puts it into the first position as the first argument to the round function, and then 2 becomes the second one, okay? So this becomes potentially an easier way of reading it. Let me kind of show it to you more clearly here, potentially. So correlates is kind of put into the first argument of this core function. The result of this is then, thanks to the next piping, put into the first position of the next function, which is round. We don't have to put the comma, we can just say 2. All right. So this can read quite nicely as correlates core round 2. So this allows you now in R, or for those of you who were using the Migrator library before, to kind of write things more left to right, the way, at least in English, we kind of write things out, okay? So it may help your code become a little bit clearer in some situations, all right? So I encourage you, if you find this is helpful and more readable, try it out. But you'd have to install the latest and greatest version of R, I think, which is 4.1.0, which only came out a couple of weeks ago. So you might just have to go back and reinstall R on your computer and then restart RStudio. So reinstall R and then just shut down RStudio, restart RStudio. It should pick up the new version of R and go with it, okay? However, at least on my computer, the new RStudio still hasn't quite figured out that this is a valid operation in R. So it gives me these little warnings everywhere and says, what are you doing here? RStudio hasn't quite figured out that this is a thing yet, okay? But maybe in the coming weeks or month or so, RStudio will have a new release and it'll understand what this is, okay? All right. So that's piping. It's now built into R. And I'll talk more about why should I do it this way or use the Migrator library. I'll talk a little bit more about that on week 17, our little miscellaneous week of odds and ends. All right. Now, I do have to warn one thing. Once you see it like this, it's very tempting for beginners to write everything like this. But I would say slow down, use it really sparingly, and when you feel like it's really adding value. In this case, I don't really like to see the code like this because I don't know the major purpose of this line until I execute this in my head. And I say, oh, you're taking the correlation of the correlates and then rounding it by 2. So in my head, I have to kind of read the middle again, then the left, and then the right to figure out what's going on. I think the better way to write this is just to write the mathematical thing we're trying to do, which is take the correlation of these four variables, our correlates, and then we're trying to round it by 2. This reads a little bit better for me, okay? I don't know about you. I'd like to kind of see how many of you like it which way. In fact, let's have a little vote. If we were to use piping, how many of you, I'll start with my example here, how many of you like to see it this way? Just to use the raise hand function and tell me, how many of you like to see it this way? Only 1, 2, 3, yay! 4, 5, 6, 7, 8, 9, 10. Okay, that's okay. All right, great. All right, at least a dozen of you, if not more. Excellent. So let me just lower all your hands. And let me ask the other question. How many of you actually, and this is subjective, so you're totally welcome to give me your opinion. How many of you like to see it this way? How many of you think this looks better? It's a subjective thing. There's no right or wrong. So you tell me, how many of you like to see it this way? All right, great. We have one brave person who admits it. All right. Thank you, Billy, for being brave. Ah, yes. Other people are now saying, yes, actually, I did like it this way. Okay. So a few of you perhaps like to see it like written out explicitly like this. Entirely up to you, whatever makes it more readable for you. All right, great. Thank you. So this is the pipe function. Sorry for the little digression, but I found that at least for this week, it really helps make my class notes a little bit more readable if I use it sparingly. All right. especially for rounding things off at the end, the aesthetic things that come after the major mathematical thing that I want to do. All right, great. So how are we using these correlates? Well, this is what we're doing this week. All right. Um, First of all, what we're going to try to do is use PCA as a dimension reduction technique. We're going to take these 4 dimensions of data: cylinders, displacement, horsepower, and weight, and we're going to somehow combine them, collapse them into one thing. All right, and that one thing, what's that one thing going to be called? This is difficult. Naming things is always very difficult. What does cylinders, displacement, horsepower, and weight tell us? It's really up to you. If you have a good answer of what to call these things, or if you want to have an opinion, just type it into the chat window. I'd love to see what some of you called it. Okay. Now I came up with a very awkward word for it. I said these things kind of capture how big and heavy this car is. Actually, I use this word, hefty. It tells me how hefty the car is. Means large, heavy, and powerful. Like if you put those concepts together in English, the word is hefty, all right? So large, powerful, and heavy in English, we call it hefty. It's like the opposite of light. So if you say like somebody's really hefty, it means that they're big, but it also means they're probably strong, like don't mess with them, okay? So similarly, I think if you call a car hefty, it means it's got some power to it, but it's also heavy. It's the opposite of a light car. Typically, when we describe a car as light in English, we're also kind of describing it as being a little bit weak in power. All right. So I said these correlates capture heftiness. If somebody had another word that you used, I'd love to hear it. Maybe it's power or strength or something else. Feel free to type it into the chat window. I'd like to hear your opinion on what you called it. Okay. So I call these 4 variables heftiness. All right. So you will see the word hefty in some of my variables coming up ahead. All right. So now, how can we reduce the dimensions of these 4 dimensional these 4 dimensions into one? Let's use PCA to do it. And the way we're going to do it is this. We're going to take our correlates and perform this eigenvalue decomposition on it. All right, let me just do it on the top of the screen. So I'm going to run eigen on it. And eigen, by the way, this function, as far as I know, does truly eigenvalue decomposition, this EVD technique of PCA, I think. All right, so, and that gives me this result called hefty eigen. That's what I'm calling it at least, all right? And so I can take a look at these vectors. Right? Once again, I'm rounding into 3 decimal places, but I can take a look at these eigenvectors. So I've got 4 variables, so I've got 4 dimensions now. It's regrettable that perhaps that the eigenfunction doesn't tell me like PC1, PC2, PC3, PC4, but the columns are actually the principal components, and each of these columns is actually a principal component. So the first principal component, the second, the third, and the fourth. Okay. And let's see what I'm doing after that. Okay. Oh, and I can also get the eigenvalues. Okay. Oops. So now, once again, the eigenvectors are simply pointing in a direction in one-dimensional space. Okay. So the eigenvectors are saying, here's a 4-dimensional cloud. I'm so sorry, I can't visualize that for you. I can only help visualize 2 dimensions. I could maybe do a 3-dimensional example one day, but not 4-dimensional example. But if you could philosophically imagine 4 dimensions, then it's saying that if you take a step in this direction, which is this first vector here, then you would have gone 1 unit in the direction of major variance. All right. And as you can see, the rows are actually representing the 4 original dimensions of the data, which were cylinders, displacement, horsepower, and weight. So it's taking about this much of a step in the cylinders direction, this much of a step in the displacement, this much in horsepower, this much in weight. So if you kind of look at these, if you go a little bit in each of these directions, then you've gone 1 step in the direction of the first principal component, the direction of major variance in this data. All right. Now, how important are these things? Well, so a couple of reminders. One is these are four vectors, and these we can think of them as column vectors, all right? So this is PC1 is top to bottom here. The leftmost column is PC1. Remember, the eigenvectors by themselves, the eigenvectors don't tell you which one is the most important. You cannot really gauge how important they are. We know that the PC1 should be the most important, but how important we cannot tell from the eigenvectors alone, because each eigenvector has the same length as all the other eigenvectors. In fact, we can calculate the length of these eigenvectors. So if you take an eigenvector, it's a vector. The magnitude or length of a vector is this formula right here. And if I compute that, so it's like it's the square of all the unit directions summed and the square root. So each of our eigenvectors has length 1. All right, so they all have just length 1. All right, so by themselves, you cannot really tell how much more important PC1 is from PC2. That's where the eigenvalues come into play. The eigenvalues actually tell us how important each of these dimensions is. Now, if I take the eigenvalues and I sum them up, can anybody tell me, if I sum up the eigenvalues here, what will the sum be? Let me grab this and move this to window 4. All right, so can anybody tell me what's the sum of these eigenvalues going to be? Anybody want to take a guess? Just type it into the chat window. Anybody? Anybody? 4. Yes, 4, 4, 4, 4, 4. Some of you have a question answer. Some of you have a positive answer. That's great. Yes. Thank you so much, everybody. The answer is 4. The eigenvalues actually add up to the number of dimensions in your original data. And we had 4 correlates, right? So it adds up to, the eigenvalues add up to 4. And what the eigenvalues are telling you is, given 4 dimensions, how much of the variance of these 4 dimensions is each of these principal components capturing? And we're told here the first principal component, and this is astonishing, the first principal component captures 3.67 dimensions worth of variance. Wow, that's capturing a lot of the dimension, a lot of the variance of these 4 dimensions. It's capturing 3.67 dimensions worth of variance. Okay, if you want to get a proportional, if you want to get like a percent idea, like what percent of the variance are we kind of capturing, then what you want to do is you want to divide each of these eigenvalues by 4, because that tells you like the ratio, how much of the 4 dimensions is each one capturing. So if I do that, so all the eigenvalues divided by the sum of the eigenvalues, so that tells me that the first principal component is capturing about 92% of the variance of these 4 dimensions. That's incredible, all right? And the other principal components are capturing 4, 5%, 2, 3%. This is captured, the last principal component is capturing only about 1%, all right? So this is what this eigenvalue decomposition does for us. It points us in the direction of the major variance and says, this is the way your data really stretches. That's where the meaning of you, that's the direction in which the most of the meaning of your data possibly is, all right? And we can do some simple principal component analysis on this now, all right? So let me go ahead and run this PR comp. All right. By the way, PR comp, I guess it stands for principal components. Okay. But it uses a slightly different estimation technique. It uses a singular value decomposition, or SVD, for those of you who are familiar with that. Okay. But it gets the same results as eigenvalue decomposition, more or less. All right. So we run this. And what can we do with it? I forgot. What can we do with it? Ah, yes, we can run a scree plot. Where is that in my code? All right. So let me just kind of show you like the summary. All right. So this is the summary it reports of this of heft PCA. So HEF-PCA gives me the eigenvectors. So once again, these are the eigenvectors. Okay. And when I run the summary, it gives me a couple of things. It gives me what it calls standard deviations. What the hell is standard deviation? Well, remember when I told you that eigenvalues are the variance of the data? Standard deviation is just the square root of the eigenvalues. And in fact, if I take this summary, if I capture this in a little variable called PCA report, and I look at these standard deviations that are reported up here, right? And if I then square them, I just take the square of them. Ooh, do these numbers look familiar? Those are my eigenvalues, okay? So when it tells you standard deviation, it's telling you the square root of the eigenvalues because the eigenvalues effectively tell you how much variance is each of these principal components capturing, right? Okay. Um, so that's just an explanation of what PR comp is reporting to you. It's giving you the eigenvectors, and if you look at the summary of it, it'll give you the eigenvalues, but it'll call them standard deviation. It'll just give the square root of it, okay? Oh, but it does give you this really nice thing that we computed by hand a moment ago, which is it kind of tells you the proportion of variance. That's what I computed by hand when I did this thing, when I did where was it? This thing, when I divided each eigenvalue by the sum of the dimensions, it gives you the proportion of variance explained. That's exactly the same thing as here, except this is to more decimal places. All right, great. Um, let's visualize this. Let's look at the scree plot. Oh, can I look at the scree plot? Because I need to give more space to the plotting function. All right, so let's look at the scree plot here. There's my scree plot. And let me just draw a horizontal line at 1 because we have one of these criteria, which is that some people use this criteria that if your eigenvalue is less than 1, you can ignore that principal component. And the reason they have this criteria is kind of intuitive. It basically says, remember the eigenvalues tell you what fraction of the 4 dimensions is captured by each of these principal components? Well, if a principal component has eigenvalue less than 1, it tells you that principal component is capturing less than one of the original dimensions of your data. So you can think of it as being fairly unuseful if it's giving you less than one of your dimensions on average. Okay, so that's just a criteria some people use. The other criteria is to look for an elbow. Look at the scree plot and see where do you get a sharp elbow. Elbow being, this thing. So, and when it's like we get this sharp drop off, and all the remaining eigenvalues. By the way, the y-axis is called variances, but by variances it means eigenvalues. So when the remaining eigenvalues kind of form a straight line, you can kind of ignore them. All right, and everything after this straight line from the elbow up, those are the important ones. That's another criteria we use, and we can call that the scree plot criteria. You actually look at it visually and say, when do this start becoming all equally useless? And ignore those and take the ones that are shooting up higher. In this case, only one principal component is like really significantly different than the rest. All right. So whichever criteria we use, eigenvalue greater than 1, or looking at the scree plot, both of them give us the same answer in this case. Not always, but in this case, that there's only one major dimension that seems to be important. And we also see that when we look at this proportion of variance. PC1 captures like 92%, 91.8, 92% of the variance of our data. Wow, we can use PC1, all right? So what we can do is we can take a look at, excuse me, we can take a look at the scores of these correlates, these hefty scores. And what this tells you is for how many cars were there in this data set again? Reduce about 390, like almost 400, 390, 400 cars. The scores, which we get from the PR comp function by just doing $x, what a unintuitive name for me, but $x gives you the scores. And what this tells you is for these nearly 400 cars, how did they score on these new dimensions? So forget the original dimensions we measured the data on. We just measured it on those dimensions because those are easy to get, right? You can go to any car manufacturer and say, how many cylinders does the car have? It's easy to report. So, but let's forget those convenient dimensions and use these more data, meaningful data-driven dimensions, PC1, PC2, PC3, PC4. And it tells you how does each car score on each of these dimensions, right? And then what we can do is we can take a look, all right? There's one thing I forgot to do in the last slide. So this PR comp, it gives us two helpful things. One is the data. The other is if you call the rotation attribute on it, it gives you the eigenvectors, okay? We can try to interpret the eigenvectors, but it's not always easy, as some of you may have found out. PC1 is like uniformly roughly 0.5 in each relative to each of the original dimensions and negative. Well, remember that these correlates, I call them hefty, meaning heavy. Well, PC1 is the opposite of cylinders, the opposite of displacement, the opposite of horsepower, the opposite of weight. So as PC1, as that number gets bigger and bigger, as PC1 score gets bigger and bigger, we're actually going in the negative direction of all of these original attributes: cylinders, displacement, horsepower, and weight. So these four attributes, if I describe them as hefty or powerful, then PC1 actually is scoring them in the reverse direction. It's scoring them negatively. So I would call PC1 how light the car is, okay? So if the score of PC1 is bigger, then it's a lighter car, because as the scores of PC1 get bigger, we're moving in the smaller direction of cylinders, displacement, horsepower, and weight. All right. So I interpreted PC1 as telling me how light the car is. Is that any questions about this? If you have a question, please go ahead, type it into the chat window, and I'll take a look in a second, or raise your hand. I'll just mention something briefly here. Depending on which package or function in R you're using, or which computer you're on, like is it a Mac or a Windows, is it Intel or some other chipset, the sign of these eigenvectors could change. The numbers should remain roughly the same, but it's possible that some of you are going to run the exact same analysis and these will all be positive, okay? In which case you may have to interpret them slightly differently, all right? That said, basically don't expect the signs of your eigenvectors, the directions in which they're pointing, to be uniform across computers or operating systems or programming languages or even like eigenvalue functions. There's a couple of other eigenvalue functions, principal component analysis functions I'll introduce you to today maybe, and they often report like the opposite sign. So I'm sorry, but that's kind of a computational detail of how these are computed, okay? So once again, computers are not perfect, right? Just as we saw in the first week of class, they don't give us infinite precision. They kind of round things off to the, depending on your computer, the 16th or the 22nd decimal place, and you don't get these perfect zeros. Similarly, when it's doing this kind of eigenvalue decomposition or SVD, the signs can actually flip based on how the code was written, what kind of hardware and software you're running it on, okay? So don't take the positive and negative too seriously, but you do have to interpret it correctly for your machine. Okay, we have a question. I'm going to try to read it out, all right? So the question from Halim is it possible if the proportion of variance distributed equally for each PC? Whoa! Is it, Guild, are you asking the same thing? If PC1 has greater proportion of variance, The distribution will be more average between the factors. Guild, I'll get to your question. It is the same question effectively, Guild? Okay. If it's not, then please, I'll give you a second to tell me more. But let me go to Halim's question. Is it possible for all the variances, like all the, Halim, could I ask you to take your mic, just turn your mic on for a second? Let's play a little thought experiment here. Let's play a little thought experiment. Let's say I challenged you and I asked you, produce a data set where all the principal components will be like roughly the same meaning. How would you do that? Is difficult? Does anybody have a guess? If I was to ask you, produce a data set, you can simulate it if you want. It doesn't have to be a real data set. If you want to create a data such that the principal components were all almost the same meaning, not exactly, but all roughly the same meaning, how might you do it? Anybody want to take a guess? You can tap it into the chat window. Halim, do you have a guess? Um, Not yet. Not yet. Okay. Okay. We'll play with this. We'll play with this idea a little bit later. Okay. So Halim, I want you to stay curious for a little while longer. Okay. And maybe after a few slides, I'll get to this question. Actually, fantastic. Okay. I'm gonna just turn your microphone off. Oops. Yeah. Did I mute you? Yeah. I'm gonna mute you. Okay. Guild, did you have roughly the same question or was it slightly different? It was roughly the same question, right? Oh, 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 I see. Yeah, got it. Okay, okay, okay. All right. I'll get to that as well. I'll just mute you for a second. So, Gil's question, I think, is like if the first PC is really big, then do the rest become kind of roughly the same? It's actually possible to have two or three or four or more big dimensions. It's possible. But after some point, you do get these diminishing returns, okay? And these remaining ones is what we call the scree. Remember, like if you have a mountain, the rubble in the bottom, which is kind of has a little slope to it, is called a scree. That's why I call the scree plot. It is true that the last several PCs often have roughly the same meaning, but decreasing a little bit each time. All right. Okay, and we'll take a look at that as well in a second. Jamming is his question. So, is it common that I observe eigencorrelates values and pre-rcomp correlates have different direction even in the same column? Yes, it is possible, Jamming. It is possible. In fact, depending on which PCA function you're using, they could all point in. The vectors will be on the same line, but the direction of the vector could be the opposite depending on if you're using PR comp or eigen or what are you. It could be the same, it could be different, okay? And it's for several reasons. One is that there are different algorithms to estimate them. You know, EVD, eigenvalue decomposition is one, SVD is one, there's others as well. But then how that algorithm was coded on the computer, like the code itself, the software itself, makes a difference. Now, a lot of software like R, oftentimes, not always, but oftentimes, it doesn't do the vector mathematics, vector matrix computation. It doesn't do it by itself. It asks the operating system, like Mac OS or Windows, hey, can you do this for me because you have some underlying libraries to do this? Or possibly your operating system, Linux, Windows, Mac, comes with libraries for your CPU. Like if you're using Intel or AMD, depending on the CPU you're using, it'll have its own libraries to do linear algebra, vector math more efficiently. So depending on which underlying system level library it's using to do linear algebra, you could get a different answer, all right? And it gets more complicated than that even. There's several other factors which all kind of multiply together, and depending on which combination of all these things you have, your eigenvectors could be pointing in different directions. So unfortunately, you cannot rely that just because you've written your R code one way, that you're going to get the same results even for the same library. So jamming your question, you're right. If you use eigen or PR comp, you could get different directions, but the same values, same eigenvalues, and the eigenvector should have the same numerical values. The sign, the valence could be different. But if you went to your friend's computer and ran the same code, you could actually get a different direction as well if their computer is using a different linear algebra library as well. So it gets really complicated, okay? So this is one of the problems with computation. We come into computational statistics and machine learning and data science thinking, wow, computers are these perfect computational creatures. No, there's many layers of abstraction and complication. So you will not always get the same results, but the numerical value should be similar. Yeah, so great question. So PC1 shows positive direction in another device. Can we still call it lightness? Jamming, possibly not. I just did it for this example, okay? So because if I told you it's heaviness and then it's pointing in the wrong direction, it might be confusing for you. So this is a fantastic point, jamming. You might be just better off picking what to call it and then ignoring whether it's negative or positive. So that's a very unsatisfying answer. So but my answer is basically, in reality, you're better off just picking a name for it and not caring if it's negative or positive, because it will change depending on which computer it's running on. Wow, what a messy world we live in. All right, so sorry to be the bearer of unhappy news. Okay, fantastic questions, by the way. Fantastic questions. Okay, all right, let's move on. So how are we going to use this? Um, so effectively, what we are going to be doing is we have these heft scores. Let me just stop the visualization. All right, so we have these scores, and again, they're all negative here because this eigenvector was pointing in the negative direction. So these are telling me like, so if I consider it lightness, then this is a heavy car. This is a very light car. Okay, if I was to be faithful to that naming, but as Jamming points out, it's not safe to be faithful to that naming for very long. All right. Now, okay, so what I could do here is, and the idea is that, where are we? Dimension reduction. Yes. Okay. So what I could do is I could take PC1, just the scores of PC1, forget all the other principal components, because PC1 captures 92% of the meaning in this data. Forget the others. This is good. This is really good. And this lightness variable now tells me how heavy or light these cars are. All right. I've effectively collapsed these four dimensions into one dimension. Well, there's three other principal components, but they're so meaningless, I can just forget them according to that scree plot, right? According to that scree plot, they're so meaningless, I could just forget them, and PC1 captures 92% of the meaning of my data, all right? And this is an example of dimension reduction, all right? Where we've just reoriented the dimensions to match the major dimensions of our directions of stretch of our data. And now we don't need so many dimensions, because like the first one or the second or the first one, two, or three dimensions probably captures most of the variance of my data anyway. All right. Okay. And what I can do now is I can rerun my regression. So I'm just going to show it on screen. I'm not going to rerun it in person again. Is if I show this on screen, then, well, let me rerun it. Let me just show you it really runs. Okay. So if I did my full regression, my earlier full regression was miles per gallon over the four correlates, which are heavily collinear, and the three remaining variables. Then in my summary, I kind of get these weird results where like these four correlates are almost zero, and horsepower gets some credit and weight gets a lot of credit, okay? But it's kind of unsatisfying because we know that cylinders and displacement are heavily meaningful to miles per gallon, but there's so much multicollinearity, they get almost zero coefficients. So unsatisfying. What I could do instead now is rerun this regression, remove those four original correlates, and replace them with PC1, which I called lightness, right? PC1, the scores of PC1 is going to be now the how light these cars are. Lightness here captures more than just the weight of the car. It also captures, in the English sense, how powerful or unpowerful this car is. Okay, so I've kind of captured all those dimensions with this one principal component. And now, if you take a look at this, and let me jump back to the slides to show you. Look at that regression coefficient. Oh my God, it's huge. It's like 0.82 because it's such a powerful explanation because it captures those four variables. At least it captures 92% of the variance of those four variables. Okay. So what we're seeing here is an example of two things. One is dimension reduction. We can take many, many dimensions of data and just reduce them to a smaller number. Here I chose one dimension, PC1. It's possible that I have examples, we'll look at that later in a moment, where we have two or three meaningful principal components. So maybe we cannot collapse to one dimension, but we can at least collapse it down a little bit or a lot of it. Okay, so that's dimension reduction. And a great use of that is to resolve multicollinearity problems, all right, as you can see here. This demonstration is also another demonstration of what we called composite measurement. And I talked about that last week a little bit. So in composite measurements, we essentially have multiple measurements of some phenomenon, and we just kind of put them together in some way, all right? We put them together in some way. And the way we put them together this time is we took these four dimensions of our original, these four variables we measured, and we put them together as PC1. And PC1 is just a composite. I just kind of added different components of each of these items together, and I created this PC1. And this is my statistical representation, or this is the construct that represents this overall concept of heftiness or lightness or whatever you want to call it. Okay. And we call this a composite measurement because what a composite does is it takes a weighted average of the original dimensions. It takes a weighted average. So PC1 is actually a weighted average. I've taken cylinders, multiplied it by some weight, added that to displacement, multiplied by some weight, etc., etc. Okay, that's all I've really done. That's what PC1 is. Would anyone like to take a guess? I'll put the chat window up here again. Would anyone like to take a guess? What are the weights that I'm using? What is weight 1, weight 2, weight? I said I'm taking a weighted average of these to produce PC1. What are those weights? Anybody want to take a guess? I'll drink some water while you take a guess. Variance accumulation, jamming, that's a really nice guess. Not quite, but I like the way you're thinking. I like the way you're thinking. I like the way you're thinking because yes, it's a term we've already. Okay, Gil, you're right. It is. I mean, I'm taking the scores of PC1, but my question is, what were the weights I used to produce those scores? All right. Yes, I'm Samakala. Oh, the eigenvector of PC1. Ding, ding, ding. Yes. And I'll show you that later, actually. I am, in fact, taking the eigenvector and using these as the weights. I'm literally using these as the weights. Okay. So PC1 is really the original dimensions multiplied by these weights. And that's giving me my scores of PC1. All right. That's how I'm compositing them together. And I'll take a look at that in greater detail in a moment. Okay. So do keep that in mind. Really nice. Okay. Fantastic. Great, 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 great. Okay. So thank you for those wonderful responses. Okay. Um, and so this is why I love to have a little bit of interaction because sometimes somebody gives a wrong answer, but it helps somebody else get the right answer. That's the beauty of wrong answers. Okay, and this is why I always say, and maybe sometimes in Taiwan we don't encourage this enough in schools, but I love wrong answers because without those wrong answers, somebody else could not guess the right answer possibly. Okay, so I love it. I love it. I love it. Thank you so much. Great. Let's move on. So this is what we're doing, right? So now one more attempt at solving multicollinearity without dropping variables this time. So Gil, this answers the question you had maybe one or two lectures ago about couldn't we put them together? We just did. All right. How do we weight them? How do we, and remember we asked, how do we weight them? Where do we find the weights? Do we just give each one an equal weight, unit weighting? Or do we use some, or do I use some domain expertise and say weight is more important, cylinders is more important? Do I use some expertise? That's another way. But principal eigenvectors, they give me a data-driven answer. Like this gives me a data-driven answer. The data is telling me what weights to use. So I don't have to use any, I may be biased as an expert or something else, but I'm just letting the data answer the question. This is not always the best thing to do, by the way. This is not always the best thing to do. But this is one way to do it. It's just let the data give you the answers. Let the computation, let the computer give you the answers without you giving your opinion on it. Okay. Not always the best thing to do because it's possible and usually the case that your data is heavily biased in some way. Okay. Because again, it was collected by humans. We make a lot of mistakes in measurement. So, but it is, if you had to let the data and the computer give you the answer, this is the way to do it. Okay. One way to do it. There are others. Cool. Let's move to the security example that I gave you for the homework assignments, okay? So in the security example, let me close some of these off. Let's go to, what's the next thing we're gonna do? We're gonna do PCA using the security data sets. Ooh, that's not very big at all, is it? All right, let's take a look. So let's load the security data sets, and I did the long and lazy way, which is I just converted the Excel sheet into a CSV. I love that some of you found like the function to read the Excel spreadsheet as well. Okay. Some of you may have also found, and I saw this on the discussion board, and I love that you mentioned this. Some of you found that you can actually go to file, what was it, open file or open data? Oh, I can't remember which one it was. There's a menu-driven way of doing it. And what you said is you can load an Excel sheet through the menu system, and that will actually print out the code for you on your console to tell you how to do it through code. I was like, wow, that's awesome. So now then you get the code as well. So that's great. Okay. So I love that some of you went, the extra mile to find these answers. I was like, no, I got to solve the homework quickly, and I just saved it as a CSV. All right. Okay. So we have these 18 questions that by the way, this is a real survey. I think I'm the one who made that survey. So we actually asked this question to consumers of like online, e-commerce services and stuff like that. We asked them all these questions about how do you kind of like, what is important to you? Like, how is security important to you in terms of like using e-commerce services? And we asked these like 18 questions or so. All right, and so we can do this kind of eigenvalue analysis. By the way, I'm using the eigen function this time instead of prcomp, and notice that I'm passing into it the correlation matrix because the correlation kind of standardizes everything. All right, correlation is like super, it standardizes everything in every dimension. So I'm kind of just taking the correlation matrix. It'll give me the same answer as if I take PR comp of the scaled data set. It'll give me the same answer, okay? So you can use PR comp. I'm using eigen, why not? All right, and so here are my eigenvalues, all right? And I can do the scree plot the hard way. I'm not using the scree plot function here, notice I'm using the plot function, and I'm literally plotting the eigenvalues because that's what scree plot does. It plots the eigenvalues. The axes are a little screwed up, so I can redraw the axis myself. You could do this with the scree plot function, does this all for you. But I've literally recreated the scree plot function using just the regular plot function. I'm plotting the eigenvalues because those are my scree plot calls these variances because that's what the eigenvalues effectively are. All right. So there's my scree plot, and let me draw my little eigenvalue equals 1 horizontal line on there. All right. So this is telling me, what is this telling me? Oof. Well, if I use the eigenvalue greater than 1 criteria, it's telling me that there is exactly 3 dimensions, 3 principal components, which are meaningful, whose variance is more than the average variance of these 18 dimensions. All right. That's the eigenvalue greater than one criteria. That's the logic behind it, is that these principal components have, each of them has captures more variance than the average of these 18 dimensions. Okay. Um, what if I try to use the elbow or the scree plot criteria? Oof, it's a little difficult because the scree plot criteria says start on the right and see how many of them follow like a straight line. Like how many of these eigenvalues like follow the straight, slightly increasing line. And then, anything that doesn't hit that line, pick those. So it's possible that I can use that criteria to like draw a straight line through these. When does it stop being a straight line? Maybe it's the same. Maybe it stops being a straight line at, eigenvalue principal component 4. So again, maybe I would pick these three. But that's with my eyeballs. Maybe if you took a ruler and eyeballed it yourself, some of you may say, well, PC3 and PC4 are like so ridiculously close to each other. Why would we take PC3 and not PC4? That's so arbitrary. Ouch. It's also possible some of you would say PC2 and PC3 are so similar. Why take PC? If you're going to drop PC3, drop PC2. Just stick with one PC. What's the problem? Look, it's so different from the others. And we kind of end up playing this very arbitrary game of like who's drawing their line which way and and who's interpreting. It gets a little bit subjectively. There isn't always a clean elbow. So the scree plot criteria is kind of hard to follow. The eigenvalue greater than one criteria can seem very arbitrary, right? Like PC3, PC4, not that different. All right. What else? Um, the other issue is if we look at the rotations, I could have here like just really looked at the SEC eigen dollar vectors. I could have looked at this, but the only unfortunate thing about this is the eigenvectors doesn't give me nice column and row labels. Damn it. So I'm going to use PR comp. I should get pretty much the same results, okay? Round it to 2 decimal places. And by the way, notice here, this is the kind of stuff where I find piping is really helpful. This rounding stuff is some aesthetic stuff. I don't want to see it in the main thing that I'm doing. The main thing I'm doing is this, okay? So I'm not going to use any piping in the front part of it. I'm going to use piping for some of the aesthetic stuff in the bottom, in the back, right? Anyway, these are the first three principal components. I'm not going to look at the first 10 because let's say I use the eigenvalue greater than one criteria or something. Let's look at the first three. If I look at the first three, I got some really bad news, and I think a lot of you saw this. How do you interpret these principal components? It's so difficult. Like PC1 has like 0.2 in every single one of these directions. It's like almost like an average of these 18 dimensions, right? PC1 is almost an average of these 18 dimensions. It's so hard to interpret PC1. It's like almost the same weight in these 18 directions, in 18 dimensions. So yeah, I could take PC1. It captures, what does it capture? It captures a whopping 93% of the variance of my 18 dimensions. Is now that's why piece principal components is so powerful. I have 18 dimensions of data, and PC1 captures 93% of the variance. That's why piece principal components is so powerful. PC2, PC3 just capture like, um, a couple of 1 or 2 percentage points each. I have to divide these eigenvalues by 18 or something. Well, not 93%. I'm sorry. I'm giving you the wrong impressions. Let me take this SEC PCA. I looked at the rotations. Let me also look at the summary. Look at let me just look at what this reports here. Who reports everything? Does it report standard deviations? Hold on. Hold on. Let me remove the scree plots. So I have a little bit more space to play with. Let me look at the summary of this. Okay. I'm sorry. I'm sorry. The proportional variance. It's not. I'm sorry. It's not. PC1, sorry, does not capture 93%. I misspoke. I apologize for that. It captures 51%. I was looking at the eigenvalues, and I should have been like dividing them by 18, but it captures 51% of the variance, so not 93%. Okay, and the second PC captures about 8.8 or 9%. The third captures about 6%. Okay, and the remaining capture 4, 3, 2, 1, less than 1. Okay, 1%, something like that. Okay, so the first three PCs do seem to capture the most variances. Fine, we'll go with the first three for now. Okay, um, but I'm still not happy. I'm not happy with how we are arbitrarily picking three. I don't like these criteria that much. It's a little bit subjective still. The other thing I don't like is I can't really interpret these dimensions. The first PC, I can't interpret it at all. It's like almost a perfect average. Like everything is weighted by 0.2. All right. Second PC, well, it has some meaning. It appears that I think if I had to capture it, I think I had difficulty interpreting them. So one was about authenticating that you're on the right website. Another one was about, you know, can you or can you not deny that a transaction took place? It was a little hard to come up with the meanings. Okay. So principal components by itself is so data driven that it doesn't really care about the human meaning behind these original items. And it can make interpreting principal components extremely difficult, if not impossible. In fact, interpreting PC1 is impossible because it's the same weighting on each. Okay? So I want to take a little bit of time to address some of these issues. In fact, I'm going to address one of these issues before we take a break. Okay? So allow me to address one of these issues. There's two issues. One, this scree plot and eigenvalue criteria can be very subjective. Is there a more data-driven way of asking how many dimensions there are? Because we're doing data-driven stuff anyway. The second question is there a more interpretable set of numbers I can look at instead of these eigenvectors? They're not very interpretable at all. Okay, so these are the two problems I want to solve. I want to try to solve a little bit today. I'll solve one of them, then we'll take a break. I'll solve this problem of objective way of finding the number of dimensions. Then I'll spend the rest of the lecture solving this problem. How do you interpret this stuff? How does a human being interpret these numbers? Because these numbers are from a machine and for a machine. Okay. Let me take a little water break. Okay. How do we all have some kind of objective way of finding how many dimensions should I take? I'll show you one way that's becoming increasingly popular. And it's interesting because I started using this technique after I read about it several years ago. And whenever I told it to people, my colleagues and people were like, "Really? I've never heard of it." But in the years since, it's become a very popular technique. So I'm very glad I introduced it to this class. Okay, so we're going to use a simulation technique to kind of ask how many dimensions should we use. And the simulation technique we're going to use is the following. Okay, and Halim, this might interest you because it relates to your question. All right. I'm trying to interpret the scree plot of data that I have. And I assume my data is very meaningful because, I'm an expert and I picked all these items and I'm going to do this kind of analysis. What if my data was not meaningful? In fact, what if my data was pure noise? Like just, psh, what if I presented PCA with pure noise, but I presented it a data set of noise that was the same size as our original data set. Now I'm going to go back to the decathlon data set because I want you to use the security data set for your homework. So let me use the decathlon data set because that's going to be my classroom example. Remember the decathlon data set, I had 10 variables and 33 subjects. I had 33 athletes and 10 sports that they were playing. That was the decathlon data set, okay? And let me, okay, I'm going to I'm going to close this one and I'm going to go to my remaining one. All right. So let me read this decathlon data set. And if you remember, um, I could run PR comp on this decathlon data set. Okay, and let me store that as dec PCA for a moment. All right. And if I looked at a summary of dec PCA, or if I looked at the scree plot of dec PCA, just a little reminder of what we saw last week. I have to do a scree plot. How do I do this again? I forgot how the scree plot function works. Give me 1 second. How did I run a scree plot before? Oh, I just ran the scree plot on the original deck. Excuse me. Okay. No, I cannot do that. Scree plots. Oh, okay. Sorry. Scree plot deck PCS scale equals scale. Someone help me out here. Types equals lines, potentially. How did I do it here? PR comp, scale is true, and then do this type equals lines. Thank you. Yeah. So let me go back and do the deck PCA, but I forgot I have to do scale equals true, so I scale the data set. Okay, great. Now I do scree plot. Thank you, Halim. Scree plot of deck PCA and type equals lines. Ta-da! Okay. Here's my scree plots. Oh, and let me draw a little horizontal line at not 0 at 1, and let me just say LTY equals dashed. All right, great. So according to the scree plot criteria, I've got two principal, according to the eigenvalue greater than 1 criteria, I've got two principal components greater than 1. Oh, too bad for number 3. It was just on the line, just a little bit below. Too bad. If I look at the scree plot criteria, which is where you kind of draw this horizontal line, oops, the horizontal line, if I draw this line through the last components, that horizontal line stops at PC5, so technically I should take 4 principal components. Let me look for the elbow. The elbow is at 3, so I should take 2. It gets a little subjective. Okay, so it gets a little subjective. Is there a more data-driven way of doing this? Here's what we're going to do. We're going to ask the question, what if, so I was looking at this deck data set, which is like, 10 columns and 33 rows of meaningful data. All right. What if, instead of meaningful data, what if I just had garbage? I just had noise. All right. So let's simulate noise. All right. And the way we're going to do it is the following. I could do it like this. If I want to do it directly, I could do it like this. I'm going to make a data set, a data frame, where I'm going to replicate 10 times 33 random values from a normal distribution. Okay? And that should give me a data set. So if I look at the dimensionality of the deck data set, it was like 33 rows and 10 columns. If I look at the dimensionality of this noise, it's going to be the same dimensions. So it's the same size as my decathlon data set, but this time it's just random noise, not really data. Okay? Halim, I got a question for you. It's a yes or no question, so to make it easy for you. Technically, if I ran principal components analysis on this pure noise, remember it's noise, there's no meaning in the data, it's just random numbers. Shouldn't I find principal components that are roughly the same in every single direction? Yes or no? What do you think? Oh, I'm going to look in the chat window. Maybe you're chatting it there. No! He says no. Interesting. Anybody want to, let's take a little vote. Maybe you looked at the slides already. How many of you think, yeah, we should get like a scree plot that's like fairly even, because I've just created 10 random variables. Raise your hand if you think it should be roughly the same. Let me guess yes. Thank you. Okay, thank you, Guild, for guessing yes. So raise your hand if you think it should be roughly the same. Guild, a couple more people, a few people, more people. You know what? I agree with you guys. One person give me a thumbs up. Thank you so much. I agree with you because it should give me fairly even because it just all the variables are the same, just as random normal in 10 dimensions. It's like a 10-dimensional sphere, like a 10-dimensional circle, if you will. Like it's all roughly the same in every direction. The variance should be the same in every single direction, right? If I was to kind of really look at this noise data sets and kind of like plot the density of the noise in the first dimension, I should get, roughly that. In the second dimension, roughly that. Third dimension, roughly that. Like they're all basically just some kind of little bit off here and there, but they're basically all these kind of bell curve shapes. Okay. Um, how many of you? Okay, let me lower all your hands. No. Let me lower all your hands. Okay, and let me ask, how many of you think no? Halim, you have to say no now because you already said it. You can't take it back. How many of you say no? I am going to get a scree plot which is not going to be even. All right. So we got a few hands. We got a few brave people. All right. All right. All right. Any more? Some of you taking your votes back. I'm joking. All right, great. Thank you so much. So I would say the class is roughly divided. The class is roughly divided. Um, so let's do it. Let's do this thing. All right. So uh, I'm actually going to create. I'm going to create a function. So instead of like using that noise, I'm going to create this function, and it's a function that you can use on your homework assignments too. Haha. Where I'm going to create noise of a dimensionality that you tell me, n rows and p columns. Okay, and then it returns to you the eigenvalues of the noise. All right. So let's do that. Set seed. And if I run this like sim noise function, it should create that noise data set and it should tell me the 10, it should give me the 10 eigenvalues. All right. And I could do a scree plot of this, but let me go one step further because I'm just lucking out on one random draw. Let me do this 100 times. Let me create 100 data sets of pure noise with the same dimensions. Each of them has the same dimension as my decathlon data set. 100 random noise data sets. And then let me take the average of the eigenvalues of the principal components. So for PC1, I'm going to take the 100 average PC1 eigenvalues. For PC2, I'll take the 100 average PC2 eigenvalues. All right. And then so once again, a reminder that this is what the scree plot of my decathlon data set looks like. Let me draw for you the eigenvalues of the average eigenvalues of those 100 noise data sets, the average, all right? And let me draw the eigenvalue greater than 1 criteria. Take a look at that. Kind of strange, huh? The eigenvalues, even though it's random data, start increasing. I mean, the eigenvalues actually go up, all the way back to PC1. PC1, on average, across 100 noisy data sets, each of them the same dimensionality as decathlon, so you can't accuse me of giving it more data or less data. I've given it the same amount of data, all right? On average, PC1 has like an eigenvalue of 2. PC2, I mean, look at this. All the way down to almost PC5, they have it, PCA is a powerful technique, but it can pull signal out of noise. It can pull meaning out of nothing. So if we take these eigenvalues too seriously, we might be fooling ourselves. All right. So one thing that I recommend is that so one technique we use, by the way, this technique I'm using is got a name. It's called Horn's parallel analysis. Horn's, I presume the name of somebody, okay? Um, the name of this person who suggested this. Back in 1965, he suggested this technique, which is Horn suggested when you have a data set, take like 100 or more, noisy data sets of the same size, take the average, eigenvalue of them, plot it out. And what you could do is you could look at the point, you could say like, look, if I had just random garbage, I would still get eigenvalues of this size. And what you can do is say, I will only consider the principal components which beats the noise, which are higher than the noise. So I would ignore PC3, PC4 here, okay? And I would only take PC1 and PC2 potentially because they're better than what I would get if I just had garbage data, all right? So this is the technique. And I've given it step by step to you with some code to run as well. You can simulate noise, replicate it k times, let's say 100 times, take the average of each principal component's eigenvalue across those 100 runs, and then you can plot it out and just keep the principal components whose eigenvalues beat the average eigenvalue of the noisy data sets, okay? This, at least, is a slightly more objective and data-driven way, and we're using a simulation technique here, where we're just simulating noise in this case, to find a way to kind of extract how many principal components are importance, right? So this is the technique I would recommend to you. Is called parallel analysis. And there's a couple of packages out there on CRAN which actually do more than a couple probably, which do parallel analysis for you. But you can just run it yourself if you wish, like this, okay? And this gives us, it helps us solve this problem. It gives us at least an objective way to say how many principal components should we have. And we say like, look, PCA is powerful, but it's a little too powerful. We can pull meaningful principal components using this two criteria, eigenvalue greater than 1 and scree plot. We can pull principal components out of noisy data sets. So let's try to beat the noise. All right. So this is the technique. It's called parallel analysis. I'll give you a chance to do this on your next homework and play with it, okay? The code's right here. You've got very little to do. All right, cool. All right, folks, let's take a little break. I encourage you, go grab a bite to eat, get some sugar or caffeine in you as you see fit, and let's get back in here. I'm gonna stop the streaming, and I'll